Hello everyone, all my dear students. In our previous video lecture, we had seen the RS flip-flop, or we can say the SR flip-flop, by using the NAND gate and by using the NOR gate. Now, it's time to learn the new type of the flip-flop, the next generation flip-flop, and that flip-flop is the clock RS flip-flop. That flip-flop is the clock RS flip-flop. So let's go on the screen and see how the clock RS flip-flop works. If you will understand this video lecture, then hit the like button, subscribe the channel. So we are going to see the clock RS flip-flop. What we are going to see? We have to see the clock RS flip-flop, and this clock RS flip-flop is the same as that of the normal flip-flop. The clock RS flip-flop is same as that of the normal flip-flop, but along with the S and R input, the S and R input here, the third input is applied, and that third input is we call as a clock input. That third input is the clock input. So here first of all we require to see what is the clock input, how the clock affects the function of the RS flip-flop and the nature of the clock pulse. The clock is a waveform which is periodic in time. It is a string of the voltage levels, the on and off, or we can say if we consider the voltage, then it is a string of the voltages. First it is supposed to be 5 volt, then it is 0 volts, then again it is the plus 5 volt, like this. Okay, so the clock is nothing but it is a periodic waveform, and that periodic waveform we use as a third input, and that periodic waveform is having a nature, and that nature is a periodic nature. It is having the on time and it is having the off time, or you can say it is having the high time and the low time, depending on what type of the waveform we are using. Here the function of the flip-flop gets affected. Okay, so the two main types of the clocks are there: symmetrical clock pulse, and second one is we call asymmetrical clock pulse. Symmetrical clock pulse is that clock pulse, or symmetrical clock is that clock in which the on time and the off time, or in other words we can say the high time and the low time, both are same. The equal time periods, high time period and the low time period is there. If you look at the first waveform, this one, then here we get this is the on time, this one is the on time, and this is the off time. The on time T on and T off, here it is the T off, and this one is the T on. The T on and T off both are equal. I am going to write down here T on equals to T off, or we can say here it is T high, means the high time period equals to the low time period. The on time and off time, the high time and the low time of the clock are same. That clock pulse is we call as a symmetrical clock pulse. Okay, a symmetrical clock pulse is also there. The two asymmetrical clock pulse are there. First we consider what is the asymmetrical clock pulse. Asymmetrical clock pulse is that clock pulse in which the on time, or you can say the high time, is not equals to the off time, or in other word we can say the asymmetrical clock pulse is that clock pulse in which the high time and the off time, or you can say the low time, are different. So when here we consider the asymmetrical clock pulse in which here both are different. Now the second one clock pulse is here. This one is the second clock pulse in which the off time, this is the off time, or you can say the low time period TL, is greater than the T on, means the off time is greater than the on time period. If we look at the third one waveform, here on time, this one is the on time, this on time is greater than the off time, or we can say the on time is more than the off time. Okay, so these two, the first, the second one and third one, these two are we call as asymmetrical waveform. And one more thing we have to note down here, whatever the type of the waveform is there, whatever the type of waveform, it is symmetrical or it is asymmetrical, the clock cycle time is important. Here if the clock cycle time is less, it means the faster working of the digital circuit. Here we are using the clock pulse in the flip-flop because of the various reasons. From that, here the first important reason is the working time of the flip-flop is decided. Okay, so whatever the flip-flop is there, that flip-flop must perform its work within a one cycle time of the clock pulse. Okay, so the asymmetrical and symmetrical, these are the two types of the waveform. We can use the symmetrical or the asymmetrical waveform. When it is symmetrical, instead of the pulse wave, we call it as a square waveform because on time and the off time are equal. Okay, now we have to see the reasons why we are using the clock pulse or the clock in a flip-flop. The first reason is the clock pulse we use because here the clock pulse synchronizes the signal and the digital circuitry. The input signal and the digital circuitry, or when we require to use the number of circuits together, and that circuit must start their work, their function at a particular instant and finish within a one clock pulse time, then we use the clock pulse. This is we call as synchronization of a digital circuit. The second reason is if the string of the data is available, then some of the bits we have to pass, some of the bits we have to save, and some of the bits we have to ignore. So for that here we have to use the clock pulse in a circuit, or we have to use the clock. Then third one is in the digital system. Here we have to save some bits. In synchronization with the time. So therefore here we require to use the clock pulse. Okay, there is one question on this clock, and that question is, what is the clock pulse? What is the clock? Why the clock is used in a digital circuit, or why the clock is used in a flip-flop? Now we have to see the clock flip-flop using the NOR gate. Symbol of the flip-flop is drawn, and that symbol is the clock RS flip-flop. It may be by using the NAND gate, or it may be by using the NOR gate. So first we consider the concept of the clock RS flip-flop, how we have to draw the clock RS flip-flop. For that here we use the symbol of the RS flip-flop, and here with this symbol we require to use the two numbers of the AND gates. With this RS flip-flop we require to use the two numbers of the AND gate. Why we are using the two numbers of the AND gate? We are using the two numbers of the AND gate because here we have to apply the third input, and that third input is the clock input, which we had seen just before in this symbol. Okay, so I am going to draw here one AND gate, and that AND gate is for the yes input of the flip-flop. So here it is the S input. Okay, then here at lower side I am going to draw one more AND gate. So here is the second AND gate, and the second AND gate having the input, that input is the R input. Now here the second input of the first AND gate and second input of the lower AND gate we tie together and we apply one common input. That common input is we call as a clock input. Okay, so here this is the clock RS flip-flop with the help of the 2 AND gate and the RS flip-flop. Okay, so here the function is same, but due to the application of the clock pulse, here we decide when the flip-flop works and when it goes into the disable condition, it goes into the no change condition. For that, here first we consider the clock pulse is having its high time period. Clock pulse is having its high time period. Now which time period is we call as high and which time period is we call as low? That is important for us. When here this time period, if we consider this one time period is we call as the high time, or this is we call as a on time. Here this is we call high time because the voltage value of this time period is equals to plus 5 volt, and here this one time is we call as a low time. This time is we call as a low time, and here if we see at this time, here the voltage value of that waveform is equals to 0, so therefore it is a low time. Okay, so we got here the two times on time. This is the on time, or we can say here it is the high time and this one is the low time. We consider the low time first. When there is a low time of the clock pulse, means the binary value of the clock is equals to 0, and when there is a high time, the binary value of the clock pulse is equals to 1. So when I am going to say there is a low time, means here it is equals to 0, and when it is high means there is equals to 1. Okay, so here the clock pulse, we consider that clock pulse is the low time period, and at the low time period, here the input to the upper AND gate and the lower AND gate is equals to 0, means here at upper AND gate it is equals to 0, and at the lower AND gate it is equals to 0. Now we know that when any one input of the AND gate is low, then its output is equals to low. It is in the disable condition. So here input for the flip-flop S is equals to 0 and R is equals to 0. So we get here the flip-flop remains in the no change condition. We know that the flip-flop gets in the no change condition. If we not know the function of the RS flip-flop using the NOR gate and using the NAND gate, then you can watch the video lecture available at the I button. I will provide at the I button here, or I will provide its link in the description box. Okay, so here the flip-flop gets in the no change condition when the clock pulse is equals to 0. Now suppose here the clock pulse is equals to 0, the S input is equals to the S input is equals to 0 and R input is equals to 0. When S input is equals to 0, R input is equals to 0, again we get there is a no change condition. If we consider the S input is equals to 0 and the R input is equals to 1, again we get the same condition. Why? Because the one input of the lower gate, which is the clock input, and clock input is equals to 0, clock input is low, so therefore here its output is equals to low, means here the flip-flop gets in the no change condition. So whatever the input we apply to the S and R input, if the clock pulse is low, the clock is having 0 input, then here there is a no change condition. Now suppose here we apply the input, that input at the clock input, we apply the input, clock input is equals to 1, means there is a high time of the clock input. Suppose here there is a high time of the clock input, this one time, then here the one input of the upper AND gate is equals to 1 and one input of the lower AND gate is equals to 1. And now suppose S input is equals to 0, R is equals to 0. Now here again we get there is a no change condition. This no change condition occur because of the application of S input equals to 0 and R input is equals to 0. Now suppose here the S input is equals to 0 and R input is equals to 1 and clock pulse having its high time period, clock pulse is equals to 1. Okay, now clock pulse is equals to 1 and the input we applied, that inputs are like this. The S is equals to 0, R is equals to 1. It means here the S input is equals to 0 and R input is equals to 1. And as we know, when S is equals to 0, R is equals to 1, we get the output Q is equals to 0, Q bar is equals to 1 and flip-flop goes into the reset condition. Flip-flop goes into the reset condition. Now third condition we consider when the S input is equals to S input is equals to 1 and R input is equals to 0 and clock pulse is again equals to 1. The clock pulse is 1, S is equals to 1. Both the inputs of the upper AND gate are 1 1. So therefore here it produces the high output, and as one input of the lower gate is low, so therefore here the lower AND gate produces the low output. It means the S input of the flip-flop is equals to 1 and R input of the flip-flop is equals to 0. What we say? We say here the flip-flop is in the set condition producing the output Q is equals to 1 and Q bar is equals to 0. Okay, so we get the same condition, the same output state when S is equals to 0, R is equals to 1, S is equals to 1 and R is equals to 0. We get the same state, that is no change condition, when the S is equals to 0, R is equals to 0. But in these three conditions, what is the requirement? The requirement is the clock pulse is equals to 1. Okay, now again we consider the clock pulse is equals to 1 and both S and R input are 1 1. The clock pulse is equals to 1 means clock pulse is having its high time. The S is equals to 1 and R is equals to 1. Then we get here the input for the upper gate are 1 1 and the input for the lower gate are also 1 1. So the upper gate produces the high output, upper AND gate produces the high output as well as the lower AND gate produces the high output. It means S is equals to 1 and R is equals to 1. We know that when S is equals to 1, R is equals to 1, there is a invalid condition. That condition is what we call it as a invalid condition. We have here the logic diagram of the clock arrest flip-flop. We have here the logic diagram of the clock arrest flip-flop by using the NOR gate. But before going towards the working and the construction, here we have to see the two output conditions. If we apply the clock pulse, then we got the two conditions, and these two conditions are we call as the initial state of the output and the output state of the flip-flop when the clock pulse goes high. Okay, so for that purpose here we draw the clock waveform and we consider the two output conditions. We consider the clock arrest flip-flop by using the NOR gate or by using the NAND gate. This concept is applicable for the both. Now suppose here this is the time instant, this one is the time instant. At this time instant the clock pulse is equals to 0 and here there is one more time instant, here the clock pulse is equals to 1. Okay, the clock pulse is equals to 1. When the clock pulse is equals to 0, here we consider the output of the flip-flop. The previous output of the flip-flop is the Qn. Here, suppose the Qn is equals to 0 and the clock pulse goes high and the output condition of the flip-flop changes to opposite state, or you can say initially the flip-flop is in the set condition, and after this here when the clock pulse goes high, at that time here the flip-flop goes into the set condition. Means the previous output is we call as the previous output when the clock pulse is low, that output is we call as the Qn, and the output condition of the flip-flop after just the clock pulse is high, that is we call the Qn plus 1. Whatever the state of the flip-flop, either it is in the set condition or it is in the reset condition, we consider the two time instant. The first time instant is the Qn. It is the time instant just before the clock goes high. The Qn is the time instant just before the clock goes high, means this time instant here the clock pulse is equals to 0. Here also the clock pulse is equals to 0. But here this point is not just before the clock pulse is equals to 1. Okay. So we consider this one time instant, that is we call the Qn, the output state just before the clock pulse goes high, and this is the time instant here. This is the time instant after the clock, just after the clock goes high. Okay, so after this here in truth table we consider the two output conditions, the two output times. One is just before the clock goes high, that is we call the previous condition, and just after the clock goes high, that is we call the latest condition. Here we denote it by using the Qn and the Qn plus 1. So first we see what happens when the clock pulse is low. We apply the input and then we see what happens if the clock pulse is high and we apply the input. Okay, so here the truth table is slightly larger than the previous truth tables. Here we use the truth table. In that truth table we use the inputs. That inputs are again same, but the three inputs are there. First we apply the input. That input is the clock input. I am going to denote the clock by using CLK. Then the second input is the R input. We can write down here the S input also. Okay. Then third input is the S input. Then the two output conditions we consider. First one is the Qn and second one is the Qn plus 1. First one is the Qn and second one is the Qn plus 1. And here there is a state of the flip-flop, the condition of the flip-flop. So first we consider the clock pulse is equals to 0, means the clock pulse is having its low time like this. Suppose here this is the high time, this one is equals to 1 and this is the low time. Okay, so we consider the clock pulse is low and here the input we apply to the clock, that input is equals to 0. Okay, the R input we consider, R input is equals to 0, S input is equals to 0. So here when we apply the clock pulse low time, here one input of the upper AND gate and the lower AND gate both are equals to 0, 0. So here it is equals to 0, here also it is equals to 0, and as we know the flip-flop is having the input R is equals to 0, S is equals to 0, it means it remains in the no change condition, means we get here the no change condition. But if we have to see how we get the no change, then for that here we have to consider the previous state of the flip-flop. Suppose the flip-flop is in the set condition having the output Q is equals to 1 and Q bar is equals to 0, then we can say here the output was in the set condition. After application of the input, again it remains in the no change condition. So we get here the no change condition. But why we get no change condition? If we have to describe it, then we can say here the output Q is equals to 1. Q is applied as a lower input input to the lower NOR gate, so therefore here its output is equals to 0, as the NOR gate produces logically low output if its any one input is logically high. Okay, so here the output Q bar is equals to 0 and Q bar is applied as an input to the upper gate, so therefore here its output is equals to 1. Flip-flop was in the set condition. Now after this here again it goes into the reset condition. You not need to write down all this, what is the input and what is the output and why we get that output. You have to just write down when the clock pulse is equals to 0, R is equals to 0, S is equals to 0, as the output of both the AND gate are 0, 0, means R input of the RS flip-flop is 0 and S input of the RS flip-flop is 0. So here the flip-flop provides the no change condition. The flip-flop remains in the no change condition. Okay, now we consider here the other condition, that is R clock pulse is again same. R is equals to 0 and S is equals to 1. Again we get here as the clock pulse is equals to low, here the output of this upper AND gate is 0 and output of the lower AND gate is 0. As we know, the input to the NOR gate flip-flop are 0, 0. It means here its output is equals to, its output is in the no change condition. Whatever the previous state is there, that remains in the same state. Okay, now after this here we apply clock pulse is equals to 1, but before that we write down in the truth table the clock pulse is equals to 0. Whatever the value of R and S, we consider one common entry here in the truth table, either R is equals to 0 or R is equals to 1 or S is equals to 1 and S is equals to 0 or both are 1, 1. Here we get the same state and that condition is the previous condition. Means here if the flip-flop was in the set condition, it remains in the set condition. If the flip-flop was in the reset condition, it remains in the reset condition. If the output state is high, then here we can write down it is Qn and here the condition is the no change condition. If the next step we can write down, then it is clock pulse is equals to 0, then whatever the value of these two, if the flip-flop output Qn is equals to Qn is equals to 1, then it remains in the no change condition if the flip-flop is in the no change condition. Now suppose here the clock pulse is equals to 1. The clock pulse is having its high time period. Means the clock pulse is equals to 1, R is equals to 0, S is equals to 0. Clock pulse is equals to 1, R is equals to 0, S is equals to 0. Then what we get here? We get again the no change condition. How we get the no change condition? See here in the logic diagram, R input is equals to 0 means one input of the upper AND gate is equals to 0. S is equals to 0 means again one input of the lower AND gate is equals to 0. It means here input to the flip-flop are 0, 0, and as we know the flip-flop having the no change condition if the inputs are 0, 0. Okay, so we write down here the clock pulse is equals to 1, R is equals to 0, S is equals to 0, and here if the flip-flop was in the previous set condition, we get here the no change condition, means there is a last state, and here we can write down the NC. You can write down the same truth table in the different way, in that you can write down the clock input, then R input, S input, the Qn plus 1 directly, or only the Q output and the condition of the flip-flop. Okay, so as per the requirement you can change in the truth table. Now here we have to consider the next condition, and that condition is when the, for your better understanding, we remove here one output. That output is the Qn and we consider only the Qn plus 1. Okay, so here it is the Qn plus 1 and we write down here the Qn means the previous state of the flip-flop. Okay, now we consider here the clock pulse is having its high time. The R is equals to 0 and S is equals to 1. The clock pulse is high, R is equals to 0, clock pulse is equals to 1. The clock pulse is equals to 1, R is equals to 0, and the S is equals to 1. Now R is equals to 0 means one input of the upper AND gate is equals to 0, and both the inputs of the lower AND gate are 1 1. So here the upper AND gate produces low output and the lower AND gate produces the high output. And as we know, if any one input of the NOR gate is high, then its output is low. Means we get here Q bar is equals to 0. This Q bar is applied as an input to the upper NOR gate. So both the inputs of the upper NOR gate are 0 0. Here its output is equals to 1. It means here when we apply the R is equals to 0, the clock pulse R is equals to 0, S is equals to 1. The clock pulse is having its high time. Then here the flip-flop goes into the set condition as the S is equals to 1. Okay, so we write down the same state in the truth table. Clock pulse is equals to 1, R is equals to 0, S is equals to 1. Here we get Q is equals to 1, and here the condition is we call as the set condition. Okay, you may interchange the inputs in the truth table, but as the sequence is 0 0 0 1 1 0 and 1 1. Now again the clock pulse is equals to 1. The clock pulse is equals to 1, but the R input is equals to 1 and S input is equals to 0. Then we say what happens in the flip-flop output condition. Now clock pulse is equals to 1, it means one input of the upper AND gate is high and one input of the lower AND gate is high. R is equals to 1, it means both the inputs of the upper AND gate are high. So upper AND gate produces the high output and the lower AND gate produces the low output. As we know, the upper AND gate having high output means here its output is equals to 0, because here the NOR gate produces low output when its any one input is high, and here one input of this upper NOR gate is equals to 1. The Q is equals to 0. It means here the input for the lower NOR gate are 0 0. So therefore here we get Q bar is equals to 1. Means we get here this condition is the reset condition. When the clock pulse is equals to 1, R is equals to 1, S is equals to 0, we get here the Qn is Qn plus 1 is equals to 0, and here the output is the condition is the reset condition. Okay, now again we consider the clock pulse is equals to 1, but the R and S inputs are 1 1. R is 1, S is 1, and here the clock pulse is also equals to 1. Both the inputs of the upper gate are high and the lower AND gate are high. Means here it produces the upper AND gate produces high output and the lower AND gate also produces the high output. And as we know, if the input for the NOR gate flip-flop are 1 1, then its output is in invalid condition. Means here clock pulse is equals to 1, R is equals to 1, S is equals to 1, and here there is a question mark. We write down the condition is the invalid condition. Okay, so we get the same output state if we compare it with the normal RS flip-flop. Only one change is there. When the clock pulse is low, there is a no change condition. Whatever the input we apply, it may be 0 0, it may be 0 1, it may be 1 0, or it may be 1 1. Now we consider the clock RS flip-flop by using the NAND gate. Here one change is there. What is that change? Instead of applying the AND gate at the input side, we are using the NAND gate. As we had seen, the logic diagram of the NAND gate flip-flop, we are making the change in this same diagram. Here there is, suppose we consider the previous diagram. In this previous diagram, there is a short of these two input and the yes input is applied, But here in this case, instead of making a short, we apply the two inputs to the NAND gate. Okay, so here if we see the construction, then here we can say the 4 NAND gates we required. From that, here the first NAND gate is having the yes input and the second NAND gate is having the R input. The second input of the upper NAND gate means first NAND gate and the second NAND gate is common, and that common input is the clock input. That common input is the clock input. The third NAND gate having one input, which is the output of the first NAND gate, and the fourth NAND gate having the output of the second NAND gate. Okay, and the output of the third NAND gate is applied as a input, is feedback is applied as an input to the fourth NAND gate, and output of the third NAND gate is applied as an input to the third NAND gate. Okay, so we had seen the same diagram, only one change is there, and that change is we apply the clock pulse to the common input instead of making the short here at the first NAND gate, and we apply the yes input. Second NAND gate we apply the R input. Here we apply the yes, the clock input to the both. Okay, so we consider again the clock pulse is equals to 0. We consider the clock pulse is equals to 0, and here the R input is equals to 0, yes input is equals to 0. Here the output of both the NAND gates are 1 1. Why? Because 0.0 is equals to 0 and its complement is equals to 1, or we can say any one input of, if any one input of the NAND gate is low, then it produces the high output. Okay, if here we consider this flip-flop is the normal NAND gate flip-flop, and that flip-flop gets in the no change condition. How we get this flip-flop in no change condition? For that, here we consider the Q output is equals to 1, previous output, and the Q bar is equals to 0. Q is equals to 1. Q is applied to the lower gate, so therefore both the inputs of the lower NAND gate are this one, the output side NAND gate are 1 1. So here its output is equals to 0, and this 0 is applied to the upper gate. So the upper gate output Q is equals to 1. Means initially the flip-flop was in the set condition. After application of the input, here it remains again in the no change condition. Okay, so here when the clock pulse is equals to 0, R is equals to 0, S is equals to 0, here the flip-flop goes into the no change condition. Flip-flop goes into the no change condition. Now instead of this, suppose we consider the clock pulse is equals to 1. The clock pulse is equals to 1, S is equals to 0, R is equals to 0. Now see what happens. Here S is equals to 0 means output of the upper first AND gate is equals to 1, and output of the lower AND gate is also equals to 1, and again there is a no change condition. How? For that, here we again consider the flip-flop is in the set condition, having the output Q is equals to 1 and Q bar is equals to 0. Q is equals to 1, it is applied to the lower NAND gate, this one, then its output is equals to 0, and Q bar is applied to the upper NAND gate, its output is equals to 1, as one input is low. So therefore here we say the flip-flop output is in the no change condition when the S input is equals to 0, R input is equals to 0, and the clock pulse is equals to 1. Okay, so once again we write down the truth table and put the all input and their output conditions. Okay, so here the inputs we consider, first input is the clock input. First input is here, that input is the clock input. Second one is the yes input. Third one is the R input, and here the output is the Qn plus 1. Just before we had seen the concept of the Qn and the Qn plus 1. Qn is the previous state of the flip-flop just before the clock goes high, and Qn plus 1 is the state of the flip-flop just after the clock goes high. Okay, so Qn plus 1, and here we write down the condition. So clock pulse is low, whatever S and the R input, here we get the output, that output is the Qn, and the condition is we call as the NC, no change condition. When the clock pulse is equals to 1, when the clock pulse is equals to 1, the S is equals to 0, R is equals to 0, again we get the condition is the no change condition. We write down the output Qn plus 1 is equals to Qn, and here it is the NC. Then next condition we consider S is equals to 0 and R is equals to 1. When S is equals to 0, this upper NAND gate produces high output, whereas the lower one produces the low output. As we know, here any one input of the NAND gate is low, then it produces the high output. It means Q bar is equals to 1. Q bar is applied as a one input for the upper gate, so the upper output gate produces the low output, means we get Q is equals to 0. So when the clock pulse is equals to 1, S is equals to 0, R is equals to 1, we get here the output, that output is Q is equals to 0, Qn means the Q is equals to 0, and here this condition is we call as the reset condition. Okay, now we interchange the input. S is equals to 1, S is equals to 1, R is equals to 0. At that time here we get again the opposite condition. How we get opposite? Here see, one input of the lower gate is low, so here its output is equals to 1, and here both are 1 1, so therefore its output is equals to 0. The upper NAND gate having one input is low, so therefore here its output we get Q is equals to 1, and here we get Q bar is equals to 0, because both the inputs are 1 1, Q bar is equals to 0. It means clock is equals to 1, S is equals to 1, R is equals to 0, we get Qn plus 1 equals to 1, and here this condition is the set condition. If both the inputs S and R equals to 1 1, at that time here we get the invalid state. How we get the invalid condition? See here, the input to the upper NAND gate, this one gate and this one lower gate are 1 1. Here it is equals to 1, here 1 and here 1. So both having the outputs are 0 0, and here one input of this upper gate is 1 and lower gate is 1. So therefore here the upper gate tries to produce the high output, as well as the lower gate tries to produce the high output, means here 1 1 1. Here there is a question mark, and we get here this condition is the invalid condition. Okay, so in this way the clock RS flip-flop work. If you understood this video lecture, then hit the like button, subscribe the channel. Thanks for watching the video.